All right, I decided to make a video here of me um, doing the test. Everybody's taking the test. I feel just dandy making a video like this. And yeah, I just hope it helps you and you'll perform better on the retake. It doesn't bring me joy that people did poorly on this. And I feel like maybe if you got a video of me here explaining each one by one with my thoughts, maybe you'll have some epiphanies along the way. Okay? So I hope you'll make the best of this. So simplify the expression so that there are no negative exponents. Okay, so we just have all these exponent stuff that need to be combined together. So as we do this, I'm just basically thinking two or three main things. I'm thinking that I can use the letter A, considering there's A's. I could use the letter B. I always seem to use the letter B, though. That when two things that have the same base multiply together, we can add the exponents. So let's just go one property at a time and look in the numerator and ask ourselves, is this all multiplication? And the answer to that is, of course, yes. The whole numerator is just one big string of multiplying. Dot, 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 dot. So let's add the exponents on anything that has the same base. There's a 1 on this b, so that's good to keep in mind. But we've got an a cubed times an a to the fourth, giving us a to the seventh. Added the exponents, of course. We've got a b to the negative 2 and a b to the 1. So negative 2 plus 1 is negative 1. There is this lonesome 2, right? And there's no other numbers that it's multiplying with. So I guess I'll just leave that out in front. I should have probably said that first, but I'll squeeze it in there. And then we've got the c to the fourth and the c to the negative 2. So we're going to add those exponents together. 4 plus negative 2 is 2, because it's just 4 minus 2. So that's c squared. And then in the denominator, there's nothing with like bases. So we're just chilling. And well, we did what we could in the numerator so far. So then there's another property that is, of course, very similar, that if you're dividing, you can subtract the exponents. Okay, so we can subtract the exponents. So do we see anything with like bases? I mean, the 2 is just sort of along for the ride here. We have an A and no other A's, so there's nothing to combine there. And I guess I'm not going to have a fraction anymore, right? Like, I'm trying to combine the B's and the C's here. So we have a negative 1 minus, be careful with the negatives, minus negative 3. That's a plus 3. So negative 1 plus 3 is b squared. And then we have c squared, and the 2 minus the negative 1, that's a plus 1. So that's a 3. And that's all squared. Yeah? I'm going to pull up the answer key just in case I make a whoopsies along the way. I'm a person just like you. So then this last one, when we have a power raised to a power, we can multiply those exponents. So 2 squared is, of course, just 4. But a to the 7th squared is a to the 14th. B squared squared, 2 times 2 is 4. C cubed squared, 3 times 2 is 6. So a to the 14th, b to the 4th, c to the 6th. And the 2 got squared to be a 4. I mean, it's a great problem that makes you use each and every property. All right. Evaluate the logarithmic expression. So natural log is, of course, log base e. And what we're asking ourselves here, or what we've been preaching, is that, let me just get rid of that, is that, well, if you take log base b of b to the yada yada, the exponential and the logarithmic are inverses of each other and just canceling it out, leaving us with the yada yada, right? So basically, this is log base e, and I want to rewrite this fraction as e raised to some power. And that power will be the answer, right? Another thing to say about a logarithm is that a logarithm solves for a power. And by that I mean, if log base b of x equals y, then b to the y equals x. The log of x is y. Y is the exponent. A logarithm solves for a power. And, there are really easy logs or they're meant to be easy logs that we can evaluate, such as log base 4 of 16. Why is log base, this is a quick and easy one, it's 2. Because we're saying 4 squared is 16. A logarithm solves for a power. We're saying 4 raised to the power of 2 gives us this 16. So here, we're saying e raised to what power will give us this fraction? E raised to what power gives us this fraction? This messy fraction here. So what is it? Well, I'm going to focus on the fraction, and what can we do with it? Well, a square root is a power, right? This is a root of size 2. We can rewrite this as e to the 9 halves. The 9 stays in the numerator, and because it's a root, we can have, those are equivalent, right? I'm tripping over my words. I'm sorry. It's only problem 2. Right? When we take the nth root of b to the m, right? Whether it's a square root, cube root, fourth root, this is b to the m over n. So n in this case was 2 because it's a square root. And m in this case was the 9 because we're raising it to the 9th power. And then there's another property that if you have something in the denominator, you can rewrite it using a negative power. Sort of like what was happening in problem 1, right? Because you realize how this one got, well, I don't need to get distracted with making analogies. So we can write this as e to the negative 9 over 2. So wait, what's happening? This natural log is log base e of e to the negative 9 over 2. So e raised to what power gives us this? Negative 9 over 2. Another way to think of this is these are canceling out, leaving us with the negative 9 over 2. All right. The idea here is every time we're trying to evaluate a log, we're asking ourselves, this base, what power do I need to raise this base to that would give me 1/3, right? When I looked at this, I said why e? Because it's natural log. E needs to be raised to what power to give me 1 over the square root of e to the 9th? Well, 1 over the square root of e to the 9th is equal to e to the negative 9 halves. So this question mark, was negative 9 halves. So 3 raised to what power gives us 1/3? That ought to be pretty quick. 3 to the negative 1. The negative 1 tells you to take the reciprocal and make it a 1/3. Let's find another one like that, just to kind of do them all in the same train of thought. Right here, we're asking ourselves 7 raised to what power is equal to this? Can this be rewritten with a base of 7? Apparently it must be, right? 7, we can raise 7 to some power that would give me this. Well, I know, let's think about this in a different puzzling way here. Let's come at it from a different direction. Well, I know 7 squared is 49, right? I know 7 squared is 49. But what would give me a 4th root if the power had a 4th in it? So just combine those two facts together. If I square it, but also have a 4th, it would give me the 4th root of 49, right? This is squaring the 7, while this 4 is making it right? So, the power has to be 2/4. But 2/4 simplifies to 1/2. Go back and watch. If you need to hear that again, go back and watch 2, 3, 4 again, or find another video if you don't like the way I'm putting it into words. But like the same thing is happening in all of those. But I hope I'm saying something that's giving you a bit of a revelation there. All right. Number 4 just says evaluate, meaning just plug x in, right? So 6 times 3 to the negative 2, just plug in x, right? So that's going to be 6 times, what is 3 to the negative 2? Well, 3 squared is 9, but 3 to the negative 2 is a 1/9. So that becomes 6/9, which reduces to 2/3. Which of the following expressions is equivalent? One more test here of our exponent property skills, right? All of these questions are exponent properties just kind of intertwined throughout. Well, if you have a power raised to a power, you can multiply. Yeah. None of these look quite right. Like this has it backwards. Why would the 7 be randomly out in front? 7/2 is not the same thing as 7, or 7 and a half is not the same thing as 7/2. I guess that leaves me with option C. But why is option C right? Because, well, the square root of x to the 7th, if you think about our, right, sorry, if you think about what that means, it's x times x times x times x times x, right? There's 1, 2, 3, 4, 5, 6, 7. Yeah, so there's a group of 2, there's a group of 2, there's a group of 2. Aha, x cubed times root x, right? The 1x left over. You could arrive at that answer a couple of different ways, right? You could come with that a couple of different ways. You could think of this as x to the, because 7.5 is wrong, but 3.5 isn't. 3.5 isn't wrong. So wait, what? Yeah, 3.5 isn't wrong. So this is x cubed times the square, right? Like, it's another way to look at that. Kind of interesting, right? Kind of interesting, right? Okay. Solve the equation for x. All right, just solving. You did this when your parents were here, your guardians, whatever, right? Not everyone's parents, of course, were here, but you know what I'm talking about. That was the day we were really solving pretty aggressively. Just inverse, inverse, inverse. So divide by 8. And then exponentiate. Why am I using e? Because it's natural log. And then subtract 3. The inverse of multiplying is dividing. The inverse of a log is exponentiating. The inverse of addition is subtraction. And I have my final answer. E to the 17/8 minus 3. Solve the equation again, except it's an exponential. So if I have an exponential, how do I get rid of that? With a logarithm. So I can take the natural log of each side. Taking the natural log of the exponential cancels out, and I'm left with negative x equals natural log 0.145. You could think of this technically as a -1. I don't know how you want to think about it, but we're just really dividing by -1, and x equals negative natural log 0.145. We just needed to move that negative to the other side. Solve the logarithmic equation again. This one's pretty basic though. Also, you know, I can't help but think like, what is a log, right? Like, let's go back to that thought. Like, why is log base 4 of 16 2? Right? Like, if someone asks you, hey, what's log base 4 of 16? You should be thinking, okay, I raise 4 to a power, and it's going to give me 16. I raise 4 to the power of 2. And 4 squared would, of course, give me 16. Okay, great. So this is saying, what's the base of this logarithm? That might be the toughest part. This is log base 10. So this is saying 10 raised to the power of -3 would give me x. It's another way to think of this, right? Because you might be thinking like, Mr. Skis, why are you, like, can you just, what's the inverse of a log? Exponentiate, right? Sure, that's the right answer. But also, like, this is so simple of an equation that it's like we can take a step back and like it's okay to like learn math, right? I think sometimes we just like want to be told what to do. It's just like, tell me what to do, right? But it's just like, what are we're trying to solve for x, right? Like, what is x, right? We're saying 10. What does a log solve for? A power. 10 raised to this power will give me x. Wait, that's the same. Suddenly, right? Like, it's a different. I feel like it's two completely different thoughts that are headed into the exact same direction or destination, right? I don't know. I hope you see what I'm going for. Just think it's interesting. Low battery, 5%. I gotta pause the video. All right, I'm like tethered to the wall here, so I'm like, I kind of turned the camera so you could see me, but I got my cord here. So where did we leave off? We solved that equation. Okay, let's keep going. The graph of the function f equals b to the x and the graph of g equals log base b of x are related in which of the following ways? So when we first graphed a log equation, right, I think I had you graph 2 to the x, and that was, 2 to the 1 is 2, and 2 squared is 4, and 2 cubed is 8, and 2 to the 4th is 16. And then I just simply told you to swap those points around. 2, 1, 4, 2, 8, 3, and 16, 4, and to plot them. Do you remember this? Is this coming back to you at all, right? We had an exponential, and when we plotted these, right, this one's probably an easy graph, but when we plotted these, we had 2, 1, 4, 2, and it started to look like this. And I did a lap around the room. It's a reflection across the line y equals x. All right, use the properties of logarithms to condense the expression. Okay, so there are several properties at play here. We have this property. What letters was I using? I think, was I using, what letters did I use when we did the notes? I want to say this was an M and this was an N. Yeah. When you have a logarithm being multiplied by a number like n, this number can turn into a power. Okay? And because this is the inverse of exponentials, in class, I said, hey, do you remember this property, right? When you have a power raised to a power, you're able to multiply them together. Well, now it's just the inverse. If we are multiplying a logarithm, we can turn that into a power. It's kind of like the same idea. These two properties are very related. Okay, and then there was another property where if we're subtracting or if we're adding two very similar situations, you can either divide or you can multiply, right? So if you have these properties memorized, they're really not that hard to apply. And the only thing that makes it a little subtle and a little more difficult to apply is the order in which you apply them. and you just want to follow your order of operations. Do not do the subtraction property first. You need to handle the multiplying by n, which is 7 and 5 in this case, first. You need to handle the multiplication before you do the subtraction. So when we make this a power, I'm going to erase these now that I've sort of said them aloud. When we make this a power, we get this, and we get this. Now, something that's true is that this is the same thing as that. If you're raising x times y to the 7th power, and why is that? Let's use a smaller number. Like if I said I was doing x times y to the 3rd power, what does that mean? I'm doing xy times xy times xy. And when you do xy times xy times xy, that means you're going to end up with 3 x's apiece and 3 y's apiece. Oh, at the end of the day, it just means cube both things on the inside. That's really what that's saying to do. Now, that's not the case for, right? There's a big difference between this versus this, right? Because this is multiplication, x times y, this is xy, 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 giving me x cubed, y cubed. But this is x plus y times x plus y times x plus y. And we know that when we do x, right, we have to FOIL. Big difference. Okay? Big difference. Back on track. What's happening here? If we're subtracting, we can divide the insides. So we end up with x to the 7th, y to the 7th over y to the 5th, z to the 5th. And so those y's, 7 minus 5, right, because we're dividing. 7 minus 5 is 2. We did that earlier, right? We did that up here. When we divided, we subtracted the exponents. So when we're dividing, we're subtracting the exponents so that we get an x to the 7th y squared all over z to the 5th, which is option D, it looks like. Oh, and this is, I wanted to comment, this is one where, is it, wait a minute, isn't that what I have here? It is. I actually counted A as a correct answer as well. I thought that seemed a little unfair. It's like, I mean, we did condense. I mean, I feel like we did follow the directions if you get option A. It didn't say, like, simplify, you know what I'm saying? So I counted A as correct as well. Which of the following could be the graph of f of x equals natural log of negative x? So, what's that negative doing to our function? Well, just plug in numbers, right? Like, because I will say, you know, I looked at this question because I didn't type this test, right? It doesn't look the same, right? I didn't type the test, but we did agree on the problems. But I realized in hindsight, as I was looking at the test results, that I was like, well, you know what? I don't know if we ever did a problem where x was negative. But I have preached over and over and over, just plug in x and see what happens. And there's really only one function that makes sense. And, well, because there's only one answer, you're probably thinking, what do you mean? Of course, shut up. Okay, I'll shut up. But what is this? This is, you're looking at this and you're going, Mr. Skis, you had us say when b is less than 0 and when b is greater than 0, when a is, or actually I did a down the side, right? When a is greater than 0, a is less than 0. When b is between 0 and 1, or sorry, when b, when b is greater than 1 and when b is between 0 and 1. And that looked like this, that looked like that, that looked like this, and that looked like that. And you're probably thinking, well, none of them look like A. or D. And you're right. You're right. Sue me. Sue me. You're right. That's because there was a bit of an assumption here that this was a times log base b of x, okay, for this little chart. But what happens when suddenly we put a negative out in front of x? Well, you can't take the natural log of negative numbers, right? Does that just mean this is completely false? No. It means that when you start to plug in numbers, if you were to plug in, let's say, 2, what's natural log of negative 2? Undefined. You can't take the log of a negative number. What's natural log of negative 3? Undefined. You can't even plug in positive numbers. Plugging in positive values of x is not allowed for this function. Plugging in positive values of x is not allowed for this function. But if you plug in negative 2, plugging in a negative 2, negative 2 suddenly is a positive 2. So natural log of negative x behaves a lot like natural log of x as long as we start plugging in negative numbers instead of, it's a bit of a thinker, I will admit, right? I will admit. It's, so that means it's got to be a, right? Because natural log x would look like this, because e is, there's no negative out in front, right? There's no negative out in front. And e is a number bigger than 1. Yeah. This would be if it were reflected, right? Option D would make sense if there were a negative out in front. All right, we're doing fine. I'm trying to keep this under 30 minutes, but it looks like it's probably going to be closer to 40. All right, rewrite. This one was not too bad. This is we just need everything as bases of 2, right? So this is 2 squared. This is 2 cubed. Now this, it's not like you got to handle the cubed right? The 8 got replaced with 2 cubed. I know you know that these two things are the same. 2 squared is 4, 2 cubed is 8. But now how do we handle this cube with the x? Again, it's that property of a power to a power means that we multiply those powers together. And then after multiplying those powers together, what can we do now? Because the bases are the same, we can add the exponents together, getting us option B. Here, it wants us to expand using the property. So we just want to go in the opposite direction, so to speak. Instead of combining, like number 11, we just want to break it apart. So if we want to break this apart, these two things are multiplying one another. So that means they could have been adding instead. I could have 2 logs adding together. Because when 2 logs are adding together, that tells me to multiply the inside. So I'm just using the property in the opposite direction. If I stop there, is that one of the options? It is. No, it's not. Just kidding. I thought it was A, but it's not. It's close to A. I got a little trick there, but it needs to be plus. It of course needs to be plus. So I didn't really think it would be that easy, right? Because, well, what can we do with these powers? I can use that other property and bring that down out in front. And bring that down out in front, right? Because a multiplier can become a power, so a power could go back to multiplication, and that's going to give us option B. Use the properties to expand one more time. Okay, let's do it. This one's a little cheeky because square, like what the frick do I do with this square root of, or 6th root? Well, notice none of the, well, I guess A does. Almost none of the options, except for A, even have the 6th root anymore. What's with the dividing by 6? That's because a 6th root is the same thing as a 1/6 power. It's a 1/6 power. And what can we do with that power? We can bring it down out in front. Okay? Bring it down out in front. Now we're pretty close. I'm pretty sure it's C, right? Because it's like, what's with the sixth on the inside? It doesn't go to the inside. It goes to the outside. It's got to be C. Now you might be thinking, why do they both have a sixth? Well, that's because when this gets broken up, right, it's 1/6. This is getting broken up into log of x minus log of y, because the division can get broken up into subtraction, and then kind of technically this 1/6 could distribute. Let me show you one other thing that you could have done, is that log of that sixth root is the same thing as the sixth root of the top and bottom, which starts to maybe make option A look appealing, but it doesn't suddenly spawn into 2 logarithms, right? It's just that I'm saying this radical is equivalent to this, which then means what? Well, I have division here, right? I have division. This thing is being divided by this thing. So I could split it up into subtraction. And now, like here, the division was like trapped inside of the power. So I needed to get the power out first and then release the division. Well, here, I turned the radical into division immediately. But now each of these have a power, do they not? Each of these have a power. So now each of them can have the 1/6 brought out in front. And maybe that is a little bit better for you there. But just, this is a moment where just watch at me, I can make a lot of things make sense. Sometimes I say the right thing and suddenly it makes sense. I'm glad that it might make sense, but also you need to have the strength and the bravery to do it on your own. You got to be willing to get messy, right? And fiddle and think think about, what can I do? How can I tinker with this, right? What can I do with this radical? What do I know about radicals? I could break it apart. Right? You got to get messy. Okay. Determine the exponential function that satisfies. This was, I think, our top question, if I'm not mistaken. Lots of us doing pretty good here. You understood that, okay, we take the starting amount and we're multiplying it. It's 14%, but to go up by 14%, to multiply by 1 is to stay put. But then we need that 0.14 to go up. And voila, we've just chosen the right answer. It's option D. Considering it was one of our top questions, I don't think it's worth dwelling on. Use the properties one more time to condense. So we can turn this 4 into a power. I need to do that property first. I can turn this 3 into a power. Why do I need to do that property first? Because multiplication comes before addition. Now that I'm adding, I can instead write it as one big logarithm where this thing gets multiplied with this thing, which is option B. This one was close, but it's trying to trick me, right? Another graph, one more graph, this time of an exponential instead of a logarithm. No tricks here, right? The trick, or the hard part, was that x had a negative out in front, which was a little difficult to handle. Okay, this one is a bit more straightforward because there is no negative out in front of the x here. So we know it's growth because the 2, sadly, these are all growth. Okay, what's the 4 telling us? there were several questions on the board where I was like, okay, decide whether it's growth, decay, where's the asymptote, right? It's telling us the asymptote. It's a horizontal asymptote at 4. 1, 2, 3, 4. Okay, that one. 1, 2. That's wrong. 1, 2, 3, 4. Okay. 1, 2. Okay, that's wrong. All right, so it's a toss-up between A and C. I mean, at this point, I'm like, okay, the -2 is doing something. I don't know if I can just, like, can I tell the difference between the two? Well, if you want to get nitty-gritty about it, the -2 is moving us right to. C is further to the right than A is. So visually, I am thinking it's C. But if you don't remember that in the heat of the moment, right? This is another situation where I would just plug in a number. What happens if I plug in, I don't know. I could plug in 0. If I plugged in 0, you need to know what a negative exponent is, which, there's already been several questions with negative exponents, questions of which that we all missed. So maybe plug in a number to avoid a negative exponent, right? Maybe plug in a number like, I don't know. I mean, you could plug in 2. Just choose something. I like 4. You want to know why I like 4? Because then it gives me 4 minus 2, which is 2. I know what 2 squared is. 2 squared is 4. 4 plus 4 is 8. So when I plugged in 2, I got 8. 1, 2. 1, 2, 3, 4, 5. Huh. Did I mess something up, or am I just... Oh, I plugged in 4. I plugged in 4. I plugged in 4, not 2. When I plugged in 4, I got 8. Let's try that again. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. Ah, I knew the answer was C. I was sure of it. There we go. I'm locked in. When I plugged in 4, I got 2 squared. That's why 2 was on my mind. All right. Solving. Solve the equation. Now, in hindsight, maybe these solving ones were a little tough because both 19 and 20 required you to use a log property. If we look back at some of the solving ones in the multiple choice, 7 was a log equation, but it didn't require a property, right? Maybe you thought 7 was easy. I don't know, right? Number 9, again, solving, but didn't require a log property. So I do think these are a little tougher for that reason. But, we want to use the log property and combine these, okay? So we don't, it's not fun to have multiple logs here. So let's combine these. If we're adding, we can multiply. And of course, we would need to distribute. Multiplication always distributes. And then now I'm trying to solve for x, but I need to get rid of these logs. I've got 1 log on one side and 1 log on the other. I mean, honestly, common sense just tells me, well, if they're both the same log, I just need to set the insides equal. It's kind of like, right? You know what I'm saying? Like if we're doing the same thing to both sides, it's really, okay, then I guess the inside needs to be equal. If log of this and log of this are equal, then I guess this and or maybe I should say this and that. If log of this and log of that are equal, then I guess this and that have to be equal, right? But you could also think of it as exponentiating both sides, right? And by doing a power of 10 cancels out. But I hope common sense is, okay, if you're taking log of both sides and somehow it's coming out equal, then I guess the inside stuff, logically speaking, must therefore be equal as well. And so x equals 15 as I subtract the 4x and add the 15 over. Two more. We need to combine these logs. We can divide. Now that we've divided, we need to get rid of the log. How do we inverse a logarithm? Right? Because here it's not like, there's no like common sense here. Or is there? Right? I do think like log base 4 of what would give me 1? Log base 4 of what number would give me 1? Again, if you just, right? Can we go back to the basics of a log? What is a log? Log base 4 of something is 1. So I know that, what was the easy example I gave? Log base 4 of 16. Log base 4 of 16 is what? It's 2. How do I know it's 2? Because 4 squared is 16. So what's log base 4 of 1? 4. Because 4 to the 1 is 4. Right? We're saying, right? I just, sometimes I say it so much that it starts to be meaningless. And I'm sorry, like you can fast forward. Sometimes I start to say the same thing over and over that it suddenly becomes meaningless, even to myself. Right? Log base 4 of 16 equals what? We're asking ourselves 4 raised to what power is 16? And we know the answer has got to be 2. So when we say log base 4 of something equals 1, we're saying 4 raised to the power of 1 is equal to that something. I guess that means it's got to be 4. So that, like, yes, 4 to the 1 is 4, right? Exponentiating cancels that out, and 4 to the 1 is 4. But also, you know, I just like to make sense of things in multiple ways, right? Not everything is just, you have to do it this one way and there's no other way to think about it, right? It's okay to take a step back and think. All right, so now we got a little fun expression on our hands. We should probably do a little, we need to get that x out of the denominator. So I'm sure for some of you, maybe a little cross multiplying feels natural. So 1 times anything is just itself. And as we multiply the 4, it does distribute. It does distribute there. And we're going to add that 8 over and get 13. We're going to subtract that 2 over and get 2x. We're going to divide the 2 and get 13 halves. Again, where did this come from? I cross multiplied just to get the x out of the denominator, right? That's kind of the trick there. All right, and last but not least, the 2000 population of Jacksonville was 736,000. And it was increasing at a rate of 1.49%. And remember, I said you could just move that decimal by 2 to turn it into the decimal representation of said percentage. So that means we're multiplying by, you know, it would be a mistake to say 1.149 because that's 14.9%, right? 0.149 is 14.9%. We don't want that, okay? We need an extra 0. And we want to know, when will the population reach 1 million? So we just need to solve this equation with some big numbers, but I don't know, get over it. We need to divide this away. Of course, the inverse of multiplication is division. We could reduce this, right? Like those are divisible by like a bunch of zeros. I know that might be a lot to think about, so I'm just going to take the time to write all the zeros. We're almost there at the final answer. If we have this exponential with a base of 1.0149, how do we, quote, cancel that out? How do we take the inverse? A logarithm with a base of 1.0149. And that's my final answer because we didn't have a calculator. If we real quickly, I didn't look at the answer key even once. So I'm going to trust that I felt pretty good about every answer, so I don't think I need to stress about that. If we look at the most missed questions, just real quick here at the end, most missed question was number 2. Yeah, again, I think this is an important one. If we touch on it one more time, we're saying log base e of this. And so we just need to rewrite this as a base of e. The radical is a denominator of 2. This exponent is a numerator of 9. And the fact that it's in the denominator means it was negative. And so the answer is -9/2. Just to stress that, since it was the most missed one. Number 5. All right. Same type of question. I hope that these have suddenly become the easier one for you after watching this video and doing some problems in class. We're saying, okay, well, I need to rewrite this as a base of 7. I know that 49 is 7 squared, and that if you have a root, you can rewrite that as a fraction, and suddenly log base 7 of 7 to the 2/4 is 2/4, which is 1/2. Number 17. I think probably just the messiness of this was intimidating, but I hope in hindsight that I hope that felt okay. I don't know if that's worth doing over again. Number 8, solving here. Did you just maybe forget the negative or something? Or maybe did log appeal to you? Maybe that's what it was. What was the most chosen wrong answer? Number 8. D, no solution. Well, the most chosen answer was the right answer, but the most chosen wrong answer was D. Okay. Number 10. That one we kind of covered pretty well. Let's look at one more, and then I'm going to call the video quits here. Number 14. Use properties to expand. Again here, what was important was that we, like, you might be thinking like, oh, both of these powers can come down and, well, none of them even tried to do that. None of them even tried to, like, I don't know, turn that 4 and 2 into an 8 or a 6 or something weird. The most chosen wrong answer for number 14 was A. What's so appealing about A? You know, what's so appealing about it? To be honest, I don't know, right? I mean, again, I think I said in the moment that it was somewhat appealing, but except not really. It's like this multiplication gets broken up into addition. So if you just mindlessly skip over the fact that that's not a plus sign, I guess that's what's appealing about it. But if these two things are multiplying, the multiplication needs to be broken up into addition. That's the whole idea of the property. That's the whole point of the property, right? So like C feels wrong and A feels wrong because why is the multiplication still multiplication, right? Why is the multiplication still multiplying? The property says that 2 logs adding can multiply, or the multiplying can be broken up into addition, right? Vice versa. You know? All right, and maybe cap it off. Last one, number 9. Solving again. Number 9, solving. This one here, right? If you just want the basics, yo, how do I cancel out this log with an exponential? Okay, but what base? Well, log with no base is the common log base 10. So if you exponentiate with a base of 10, that cancels it out, and you end up with 10 to the negative 3. You look at the options, you're like, oh, shoot, that's not one of them. So you end up saying, that's the same thing as 1 over 10 cubed. All right, get out of here. Bye-bye.